Yeah, hi everyone. Thank you for coming. Um, yeah, so this week we're going to be talking about naming and communication, and then kind of getting into the project at the end. If you're interested in it, the event is here. So you can get your points. Or you get points. Hey, you get points. I mean, they.
There's supposedly prizes, but
Yeah.
I don't know what the prize is.
There's no point. Okay, well, it's probably too late now. But, yeah.
Don't worry, bro. It's not that
Yeah, I don't know if they reset. Do you know? Did they reset every quarter, or is it year long? Okay. Okay. It was money like previous year, but I don't know. Yeah, I suppose like a gift card.
I don't think you know.
Yeah. All right. Yeah. So today we're going to be talking about the OSI seven-layer model for network communication, and then getting into communication middleware, and then obviously versus messaging and kind of how that's set up with the distributed system, and then talking a little about namespaces. Okay, so delving a little bit into what the OSI model is. Essentially, whenever you have two like hosts or computers, right? Just like a distributed system, the name implies, you need some way to communicate between them to actually do your work. So this is typically done using like some sort of network connection. And the way we break down how a network connection takes place is with the seven-layer model. You may also see like a different number layer model. Sometimes they combine some of these layers because some of them are like more abstract, I guess. Um, but yeah, the key here is that at the top, we're starting with the more kind of like hardware-oriented layers. So, for example, physical is literal kind of bits and I guess bytes that are being translated between each node in the network. Data link is between each, I believe it's between, yeah, it's between two like, physical nodes, I believe. And
He's a high schooler.
And then as we kind of go down these layers, we get to higher and higher level network layers. So for example, transport layers refers to like TCP, UDP, those kind of protocols are used in that layer to communicate between actual hosts themselves. So like each of your actual nodes where you're doing programming and running code. And then as we get even higher, we get to like application level protocols such as HTTP or SMTP, other kind of like very high level protocols that are essentially used to dictate an application level functionality that you want. Okay, cool. Yeah, and then the key here is that this is standardized. So basically it's portable between different distributed systems, right? And yeah. Any questions on that? Cool. Okay, so yeah, we talked about this a little bit, but here I've listed some of the kind of common functionality that is implemented at each layer. So just quickly running through this. As I mentioned before, the physical layer is the actual bits that are being transmitted. At the data level, you may see something like a checksum to make sure that the bits are actually still right and there's no noise introduced or something like that. Network layer generally handles like the routing of the actual bits to the destination node in the network. And then transport layer, like I mentioned before, is generally going to be your either TCP or UDP, the protocol that kind of dictates a logical connection between your one node in the network and like your final node in the network. And then these two session and presentation, I have little asterisks here because they're technically generally there's no specific protocol assigned to these two layers, but they correspond to features that are implemented generally at the application level. So per session, you want some form of synchronization between two nodes that are like physically distinct to make sure that the way that we're representing data is the same. And then for presentation, we want to make sure that we're actually understanding the bits themselves in a proper manner. So for example, maybe one host reads from left to right and the other host reads from right to left when trying to interpret the bits. So we need to make sure that they actually match up. And then finally, application layer. So this is where you can implement any additional functionality you need, maybe like authorization to make sure that a user can actually read the bits so you can like encrypt the data. Okay. And then another thing to note is that the layers are implemented in such a way such that when you send something at a high level, or using a high layer, it will kind of append these headers onto the message. And then when you're kind of actually interpreting the message, you look at the header and you kind of determine how to process it, and then kind of feed it up through the layers up to the highest layer again, um, where you can process the final header. So the reason why we do it this way is because sometimes you have like intermediate nodes in your network that are actually physically kind of redirecting the data. So, for example, this data link header can kind of contain whatever information is necessary to actually say, like, hey, I need to go to this router, hey, I need to go to this switch, right? To kind of actually move through the network as a whole. Yep.
You said that you append the header?
We put it, yeah, we add it to the front of the message.
Oh, okay.
Yep. Cool. Yeah, so we talked about this a little while ago now, but just kind of referencing a demo that we did way back when, where we had this like very simple app, where essentially on the front end we were doing a simple calculation, adding two numbers, and then we had a separate node that was actually doing the calculation, right? So if you recall, what we had to do on the front end was to make this function call to add two integers, and then essentially we used like an RPC remote procedure call that we'll get into a little bit more later. But effectively, what this is doing is it's just saying I need to basically make a call to the network here to learn how to add and actually do the addition, and then once the addition is done, it'll kind of return the result here, return it back through the network to the client end, and then render it on the website. Right. So if you recall that example or look back at the code, you'll see that we're actually making this request using HTTP. So I kind of mentioned this earlier, but it's sort of a trick question. But what layers or layer would that kind of a message be using for the OSI model?
What do you think?
Using the network layer.
Sure, yeah, the network layer will be used, but it's not the only layer that's going to be used. Try to think back to those headers, right? If you have the network layer header, what does that imply you must also have?
The data link.
Yeah, exactly. So you're going to need to have so basically it's going to use at least these three layers. But what you'll see is that since the message was using HTTP, it'll actually use all of them. Because HTTP is implemented with TCP, so it's going to be using transport layer for that. And then these two layers typically they don't have real protocols associated with them, but I'm just kind of grouping them under that definition. Does that make sense? Cool. Okay, great. Yeah, I'm going to pass it up to Daniel.
All right, now we're going to talk about communication middleware. And so we talked about this a little bit before in the previous weeks, but what a communication middleware is basically it kind of outsources the communication between nodes so that you have like a language or platform in not way to communicate. And typically services that are going to be provided is going to be like DNS. You're going to have some authentication service for like user accounts and things like that. It's typically going to provide atomicity guarantees, so that if you do distributed operation, you can guarantee that there won't be some sort of race conditions that's going to occur during that procedure. Some reliability, so like if something fails in the middle of the distributed operation, you're like modifying data, you're gonna have some guarantee that there's going to be a way to recover if like the server shuts off while writing to disk or something. And then it's typically going to have some interface like a voice procedure call to interact with this communication middleware. And so the reason to do this is that instead of having to implement the large portion of the network stack, you only really need to focus on the application layers, and your session and transfer are going to be handled by the communication middleware that you're going to be using. And so one big problem with the distributed system is like synchronization. So there's typically these two different ways we can define a communication connection. So we can say that a connection is transient or persistent. And so what transient means is that the connection is only really there if both the sender and receiver are up during the message send. So So, for example, like a real-time video connection is going to be using UDP, and that's going to be a transient connection. And so the moment one side turns off, that data is lost, and there's really no way to retrieve it. A persistent connection or a persistent communication means that even if one party is offline, you're still going to be able to receive that data sometime in the future. So, for example, email. That's what's illustrated here. So the client sends an email, it gets stored into the database, and the server doesn't necessarily have to be active when the client sends that email. When the server turns back on, it can just contact this database and retrieve the email traffic, and then decide what to do with it, and then we can send the a response to the client at some time in the future. And then we also have synchronous and asynchronous communication. If you've ever taken like your operating system class, synchronous basically just means that while this communication is going on, you're going to be blocked, so you just have to wait until you get a response from this message you're sending. And asynchronous means that you're basically sending it, and then you're doing other stuff with your process. And then once you get a response, you'll get an interrupt or something, and then you'll decide how to handle that. That's synchronous and asynchronous. And then yeah.
Okay, great. Alrighty, so we're basically going to kind of delve into what a remote procedure call actually is through the example of the same example we've been using of this kind of calculator app. So just to kind of frame this a little bit though, effectively, whenever you're trying to communicate between two nodes, you need to make use of some sort of like network call, right, to communicate between them. And generally, the way that's implemented with the distributed system is through what's known as a remote procedure call. So the key kind of intuition here is that we're effectively trying to hide the fact that whenever we're doing an operation on a node, it's being done over the networks. Right? That gets back to the concept of transparency that Daniel was talking about in a previous workshop. So effectively here, what we're doing is we're making this call to this add a plus b or a comma b, I guess, with plugging in these two parameters function. And it is doing it over the network, but the website itself doesn't have any way to directly know that this is making a call over the network, as opposed to just kind of implementing the function right here locally and then returning the result. Okay, so the first step here is to actually make the function call, like we're seeing. And then once we've done that, this function call is made to what's known as a client stub. So the client stub effectively just represents all the functionality that's present on a separate node, in this case, the server. And then, so here what the client stub will do is maybe it'll kind of format the message or add any additional headers that are required, that kind of thing. So in this case, if it's making an HTTP request, right, we need to kind of add additional HTTP headers that are required. And then here we're just kind of making use of this get function. I believe we implemented this with Python. But effectively, regardless of the specific function, this is just calling whatever network interface is present on the client to actually make the request over the network. And then here, once you make a call to that network interface, you will actually use whatever the kind of OS implementation is to and the network hardware to send the request over. And then here, once the server receives it, it will actually kind of receive the request and then route it to whatever kind of port or whatever configuration you have set up on the server process that's running to receive the request, and then the server stub will interpret the request and direct it to the actual appropriate function implementation on the server, like this. And then the server actually just returns the result, and then it'll kind of actually feedback all the way to the client. Like that. Okay. And then along the way, it's just kind of unpacking and more or less repeating the same steps in reverse. And then here the client actually gets the result implemented. So yeah, we just wanted to make sure that everything was explicitly clear with this process. Are there any questions with that? Yep.
So I'm curious how is this different from REST? I hear oftentimes like RPCs compared to REST. So like my big first question is, how do you abstract away latency and the asynchronous like call? Because I like with add, right? It looks like do you just basically stall the you know, this, like,
Uh-huh.
stall the,
Yeah.
you know, the computer while
Uh-huh.
it's waiting for, you know, to resolve, or, or is there like some other thing that RPC sort of?
Yeah, I think latency thing is kind of hard to deal with. Generally, you would like depending on on whether you want to be blocking or not. If it's blocking, then yeah, you would just have to kind of wait it out. But sometimes you can kind of if you know it's going to take a while, right? Because it's like the people implementing it know it's going to actually be over a network. They can kind of run this and then do something else. In the meantime, and then come back and check.
Okay, so the call to add is still done asynchronously. It could be.
It can be, yeah.
Okay.
So yeah, and then in terms of the REST thing that you were mentioning, from my understanding, REST is basically just a like a way to just choose how to design, like on the server side, what the interface will look like, such that like any requests that you make kind of don't carry state with it, I believe. So right?
Yeah, so like REST is basically just pretty much like modeling your like server state using HTTP to get for post request. You're basically just abstracting all your resources as like a URL path. That's kind of the philosophy for REST. You're like spending some parameters over JSON relationship bodies, I guess.
Yeah, good.
It's kind of just how much like data is coming in basically.
You're talking about REST or just obviously it does do that, but it's I guess I would say that's not the only thing that it's doing, right? It's also specifically to providing an interface to the server implementations of logic through again, I guess this client stuff. So it's more or less kind of a general architecture that does do that and does provide the interface. Okay, so yeah, some considerations when you're designing that server interface and just RPC in general. So we want to make sure that our code and our interfaces are kind of like machine independent. So what that really entails is that we want to make sure that when we're communicating, right, the language that we're using to communicate is a programming language independent. So for example, we don't really want to send over like a Python object in our message if we're not running Python on our server, right? Because then it's not going to know how to interpret that. So generally, like Daniel mentioned, with like a REST kind of setup, if it's RESTful, then we would just use JSON or some other format for our data that's standardized, and that generally in any language you could actually just like parse through and then convert it to the relevant object or whatever type you need to actually process the data. And then we also want to keep track of like big endianness versus little endianness. So this just refers to the like, actual byte ordering, or bit ordering, byte ordering, whatever. I think it's byte ordering. Basically, you just need to make sure that when you're interpreting the data, right, you're actually reading it. At the end of the day, you're literally just reading the bytes of the data. So you need to make sure you're reading it in the correct order. So generally, what you may see if you're looking at a low enough level is that you would convert the encoding, the byte encoding to whatever the network encoding is, and then the network encoding would convert the network encoding back to your local kind of encoding, even if the encodings are the same, just as kind of a matter of precaution. Okay. And then you may also want to keep in mind that just because you have access to things locally in your address space on the client, obviously if you send that over the network, the server will not have access to your local kind of data structures like that, right? So you want to make sure you're sending all the relevant data, so like no pointers or anything like that, right, to the server so it can actually process the data. And then we obviously, and generally with distributed systems, you want to make sure your client and server are both resilient to crashes so that they can actually recover and not lose state if one has a problem. Okay, any questions with any of these? Okay, cool. So then, yeah, let's delve into a couple kind of common messaging patterns that you'll see building upon RPC. So we've touched upon a couple of these before in some capacity, but yeah, the general idea is that we're going to have like a request reply pattern where we're going to send a message and then try to get an acknowledgement that confirms that it actually occurred, maybe with a result, like in the case of the add function. And then another common architecture that you'll see is this publisher subscriber model, where essentially if a client would kind of subscribe to whatever events that they want to learn about, and a server would kind of publish events to that. And then you would kind of read those in and process them as necessary. So a common example would look something like this, where we basically have two topics. The publishers can push out data to them, and then the subscribers can read from them and process the data as necessary. So like a great example of something like this would be maybe you have like 10 nodes that are processing like real time like video footage or something. And then maybe you have like 10 cameras that are kind of actually filming the data, right? Or maybe it's near real time, something like that. So each of the kind of video cameras push out data. And then once each of the worker nodes has finished processing its current like video clip or whatever it's doing, you can just pull from the relevant topic and then process the next video clip. Yep.
So I'm not sure if you're familiar with Kafka, but I think Kafka uses
Yep.
like producer consumer. Is that
Uh-huh.
the same
Yeah.
thing as publisher?
Yep. Okay, cool. And then what you'll notice here with that, and generally with like this RPC model, is that you'll have some sort of queue for your messages. And then the clients will be pulling that messages in, or pulling those messages in. And like I mentioned, this former task thing refers to the same kind of framework that I was describing with the videos. Okay, cool. Any questions there? Okay, so yeah, kind of talking a little bit about some of the interfaces for message passing. Um, what you'll generally see is that processes themselves will be divided into groups, and then each process will have like a group ID and a process ID, such that we can kind of have like a notion of worker processes, right? So that would be a group, and then each worker would have an ID, and then maybe you have the producer processes that are they have that's their group ID, and they each have their own process ID, right? So by doing it this way, we can actually have like a rigid structure for the processes that are running, and then a way to kind of establish relationships between them. Yeah, and then something that we want to consider with these interfaces is that we want to have functionality for asynchronous communication. So if we send out a message, we can kind of keep running our own code and then kind of hear back or listen in, maybe get an event or something when the request is finished running and we're getting a result. Yeah, so there are many kind of different implementations for these kind of interfaces, several open source ones. So I would encourage you guys to kind of try looking into that and let us know if you're running into any issues or have any questions about that. Cool. Okay, so yeah, a bit more about middleware. So I mentioned that we kind of have this notion of queuing or very often when we are working with distributed systems and sending messages. So this is kind of an example of what some sort of queue like that would look like. So here we effectively just the source acts like that add kind of node, and the destination acts like the server node. So we're sending a message out, and then it's kind of getting queued in this queue. And then as the message broker gets more time to process messages, it'll apply whatever rules are necessary, maybe authentication, that kind of thing. And then it would feed it throughout the outgoing queue here, and then it'll go back to the destination. And then it'll kind of repropagate in the opposite direction to get back to the source. So this gives us the ability to kind of act as an intermediary there, right? And introduce any additional steps that we may want to introduce. So maybe this is running with old hardware and we need to like modify the message in some way. This would be one way to kind of go about doing that. Like reformatting. We could also have a way to have redundancy here, right? So maybe if our destination nodes are running or very volatile or something, we can kind of resend the message because it's stored here at the broker. And then this was also another way to manage those publisher subscriber architectures, right? So we can have the queues just sitting on the message broker, even when the destinations are not ready to receive them. And then maybe the destinations kind of ping the broker to pull the latest message up the stack for you, I guess. Okay. Any questions with that? Okay, let me pass it back to Daniel then.
All right, so now we're gonna discuss how to organize your all your nodes into what are called namespaces. And so basically, when we name something, is just a way to identify a certain entity. And so an entity is like a computer, disk, or file, anything that we might need to address. And then a name is basically just a piece of data that we can use to refer to that entity. An address is the name of an access point. So like an IP address, your access point would be your physical device, but your IP address would be the name of that. And you have an identifier, which is a one-to-one mapping of an entity. This is kind of similar to an address, but the like semantics is that an identifier is going to be permanent. So for example, your MAC address is burned onto your NIC in your computer, and so you can't really change that unless you use like spoofing in your operating system to like fake it. But yeah, for all intents and purposes, like a MAC address isn't really an address; it's an identifier. And then your IP address, you can like change that every time you connect to a new network. That would be what we refer to as an address. And so a namespace is basically just a graph between nodes that basically identify the label hierarchy of our of all of our entities that we want to keep track of. And so flat namespace is very simple. All of the devices are just under one namespace, and we can load entities through broadcasting and forwarding pointers at a home location. Now, this is typically used with a distributed hash table. You just run a hash function, and you just do like a mod and however many devices, however many names underneath the namespace you have, and use like a forwarding pointer to look it up in a lookup table, and you can like find that device there. The other thing is a hierarchical namespace. So you've just probably seen this before. So the higher nodes are more stable; they're like less likely to change, and then a lower node is more likely to change. And so one example of this is like your DNS server. So like the .com servers are always going to be there. The Google.com servers are always going to be there. And a lot of the like smaller subdomains are probably going to change a lot. So like maybe Google decides to change Gmail to like gmail.google.com instead of mail.google.com. That would be lower down the hierarchy. And so each intermediate node can have multiple child nodes. And all namespaces underneath other names, basically. Let's go ahead. The ways to look up names, we have two ways: iterative resolution and recursive resolution. So iterative means that whoever wants to look up the name has to do all the requests. So on the left side, we have our local DNS, or like we have our requesting host, and it messages the local DNS server. The local DNS server is doing a recursive lookup, so it's messaging all of the DNS hierarchy itself. But like yeah, recursive resolution, our host is just asking the local DNS server, which then asks the root DNS server to do the entire resolution. And then basically just outsourcing the task to all the subservient name servers. And then attribute-based thing is basically just like a way to formalize the structure of the namespace. So essentially it's just a big table with all our names. We basically label each layer of the hierarchy with an attribute. And then the reason why you want to do this is like if you want to store the namespace inside like a table or something, instead of having to go look up each node individually in like a forwarding table, it's much easier to just look it up directly down by just, and you can do a lot of filtering too. It's much easier if it's like in a well-structured database, like man, you can just shove it into like MySQL or something. Then okay. Yeah, wait, stop. You did not put a link there. Yeah.
Well, have it.
Okay.
Well, have it.
So yeah, we're gonna do a quick demo, I guess. Alright, we're doing camera laptop.
Yeah, sure. What's up?
Good question. Where did I get the idea of a namespace? Do you mind explaining?
Okay, yeah. So like, let's go back here. So a namespace is basically just a logical way to organize your like physical resources. So for example, like in a DNS server, you have like your .com and like your subdomain, and then you're like, yeah, you have like your first section, right? Like you would go to like the .com would be a big namespace, and like Google.com would be a sub namespace underneath there. In this example, it's like XYZ Industries, and then we separate the namespace into United States and European Union. Um, and all this is we're basically just labeling each computer underneath into like an organizational structure. Similar to like if you're in a company, it's like who's your manager, who's their manager, uh, and so that way we can, if we want to find a resource, we can easily just look it up. We don't have to like do an entire broadcast, generate a lot of unnecessary network traffic. We can just do if we have like a piece of information, we can just as for example, if we say we know that this computer is in the European Union operation, we just ask them instead of having to do an entire broadcast essentially.
So is it basically just like an abstract grouping? Is this?
Yeah, literally.
So, but if you go back to a couple of slides.
Yeah.
Because I know with DNS, you're saying here with like with a flat namespace. So the flat namespace, you mentioned that there's the need for the distributed hash table.
Yeah.
But typically in DNS, as far as I'm aware, you don't need a distributed hash table because you have like a centralized like authority.
Yeah.
So why is there like what's the distinction between how I guess normally DNS works and how it may work in distributed?
Yeah, so a distributed hash table is basically like, so if you have a flat namespace, all the names are like underneath a single node. But you really need you need like a quick way to utilize this structure. And so it's not like necessarily like all the namespaces are going to be all the computers are going to be on a single layer. But it's just like looking at this and saying like how do we look it up? How do we look up our resources the fastest? And typically the way you do that is a distributed hash table, where you can just you organize like your data, um, you organize the data, basically based on the hash and the module, so that you can just like have an array and then look it up really quickly instead of having to do like a exhaustive search essentially.
So a couple questions. So is DNS an example of
No, DNS,
DNS?
yeah, it's not an example of this. Yeah, like typically a flat name system is like rarely used, it's typically hierarchical these days, but.
All right, thanks.
Okay, cool. And now we're gonna go to the project. I'm just gonna do a quick demo of Microsoft. Piece it up there. Look at.
Stop the recording. Everything.
CV, yes.
Yeah, you can.